Okay, now we're ready to state the Myhill-Nerode theorem and prove it. So we just defined this notion of equivalence of strings, which was two strings are equivalent if for every suffix that we add to them, they are either both on the language or both not on the language, right? And we proved that this is equivalent relationship and partitioned the string into equivalent classes. And now the key observation is that if x and y are equivalent, then they're indistinguishable according to the language. We proved that. In particular, if this relation have n equivalent classes, then there is a fooling set for this language with n strings, right? And the proof of that is pretty easy, right? Because for every one of the equivalent classes, right, we have the sigma star. It's partitioned into classes, and classes, from each one of them, just pick one of the strings, right? So x1, x2, x3, right? And just put them into a fooling set. x1, x2 to xn, and put them into a fooling set. And now observe that since xi and xj belong to two different equivalent classes, they are by definition distinguishable. Otherwise, they would be in the same equivalent class. So all the strings in F are distinguishable, which means that F is indeed a fooling set, which implies that, that implies that we have fooling set of the desired size. This in particular implies that if we have a language where the number of equivalent classes is infinite, then we can have an infinite fooling set for it, which implies that it's not regular. Okay. Okay, now here is the key idea leading to the Myhill-Nerode theorem. Let's assume that I have two strings x and y, and they are equivalent. Namely, they belong to the same equivalent class of L. And take any string A, right? Take any character A. And then the claim is that x of A, if I take the string x of A and y of A, those two strings also must be equivalent according to L. And the proof is kind of immediate, because if x and y are in the same equivalent class, then for every w, xw is in L, if and only if yw is in L. That was the definition of being in the same equivalent. That's the definition of being equivalent, which means they're being in the same equivalent class. And now the trick is that I'm going to write w. I'm going to restrict w to a string a w prime for some string w prime. I'm allowed to do that, right? So I get that this implies that for every string w prime, x a w prime is in L if and only if y a w prime is in L, right? This is the same. This is a restriction of what's written above. So we know this is true. But that, of course, implies that xa and ya are equivalent under L, right? Why is this interesting? Well, it implies that we can think about the equivalent, what equivalence class a string is in as being its state in the automata, right? So here's the statement. If L has n distinct equivalent classes, then there is a DFA that accepts it with exactly n states. And the definition of this DFA is somewhat abstract, but it's surprisingly simple, right? So first, the set of states is just going to be all the equivalent classes of L, right? To remind you, this was, if you remember, x, L for x in sigma star, right? So we take all the equivalent classes. Every equivalent class is going to be one state. The start state is just going to be the equivalent class of the empty string, of course, because that's what we have in the beginning. The accept state is all the equivalent classes such that x is in the language, right? Now, it's easy to observe that if we have an equivalent class according to L, either all the strings in the equivalent class are in the language, or all of them are not in the language. So that's kind of why this definition makes sense. Okay, so all the equivalent classes that belongs to L, the string belongs to L, are going to be in the accept state. And now the transition function is just what we used earlier, right? We just proved that from the equivalent class of X, given the character A, we just moved to the equivalent class of XA, right? And the previous lemma we showed proved that this is well defined. So, and now we can define the automata, right? It's just, defined using the above notation. This is the resulting DFA. It's easy to show that this is DFA that accepts L, and it's minimal because we proved that any DFA for accepting L must have number of states that is at least the number of states. At least the number of equivalent classes it has, and this DFA has exactly this number of states. So we proved the lemma, and now we can summarize what we just proved as the Myhill-Nerode theorem that says that L is regular if and only if the relationship that L defined has a finite number of equivalence classes, and if it has n equivalence classes, then there is a DFA that accepts L with exactly n states, and this is the minimum possible, which we proved. Okay. And in particular, a language is irregular if and only if it has an infinite number of equivalence classes. This now gives a new interpretation for all the stuff we did with the fooling set, right? Because what we did with fooling set, we just showed that there is we gave witnesses showing that the number of equivalent classes is infinite, and as such it was irregular. And the algorithmic implication is that if you give me an automata, then you can, in fact, for the language L, you can in fact compute the minimum equivalent automata, and this is the equivalent restatement. And I will leave you with an exercise to think about the algorithmic equivalent, how to do this. So first show that if I give you two automatas, two DFAs, you can check efficiently whether the languages are equal or not. This is easy. Next thing is to check whether or not, if you have a state Q and a state Q prime, to check whether or not those two states are equivalent, or if you want indistinguishable. This is easy to do with the first part. And now, given a DFA for a language, describe how to build the minimum automata for it. And I will give you a hint, you need to use the previous part. And that's it.